Welcome to YouTube channel Academy. In this video, we are going to discuss about KL-UCB algorithm. Here, KL divergence is the name after two mathematicians, which is Kullback and Leibler. So, in 1951, Kullback and Leibler published a paper titled On Information and Sufficiency, where they introduced the concept of KL divergence. The KL divergence has since become a fundamental concept in information theory, statistics, and machine learning. So it is called as Kullback-Leibler UCB algorithm, where KL-UCB algorithm is a popular method for solving multi-armed bandit problem, MAB problem. We call it as multi-armed bandit problems. While it can share similarities with the UCB algorithms, where UCB is a heuristic algorithm for solving the multi-armed bandit problem. And here in KL-UCB algorithm, it is an improvement over the UCB algorithm. It uses a different method to compute the upper confidence bound, which is based on Kullback-Leibler's divergence. So KL-UCB algorithm uses the formula to compute the UCB for each or each action. So the main difference between UCB and KL-UCB algorithm is KL-UCB uses a different confidence bounds, or it uses KL divergence method, and KL-UCB is more robust, and it is KL-UCB also gets better regret bounds when compared to UCB algorithm. In summary, we can say that KL-UCB algorithm is more sophisticated method for solving the multi-bounded problems, chooses the different confidence bounds, and is more robust. Here, the KL-UCB algorithm is designed to solve multi-armed bandit problem. As I already said, it is used to solve MAB problems where the agent faces a set of actions and needs to choose one action over the time to maximize the cumulative reward. So the agent, as all you know, the agent work is to choose an action to gain the maximum cumulative reward. So KL-UCB aims to balance both same exploration and exploitation. It is used to balance both exploration and exploitation. That seems promising, but our occurring actions are selected more number of times that give more cumulative rewards. So this algorithm uses the KL divergence to measure the uncertainty between empirical or observed distribution of rewards and the true reward distribution for each action. Here, KL or true actual reward of an action minus observed reward of an action. Here, for example, 25 is the actual or optimal reward that need to be obtained minus observed reward of an action A. So it then adjusts the upper confidence bounds for the actions based on this measure. Kullback-Leibler divergence is a mathematical measure that calculates the difference between two probability distributions. Let us take an example like two probability distributions P and Q over the same experiment. The given KL divergence from P to Q is defined as KL of P parallel to Q, or you can say it as, this symbol is called as divergence symbol. It is a mathematical notation that represents the Kullback-Leibler divergence between the probability of P and Q probability distributions. This is the formula. Summation of P of x of I into log of P of x of I by Q of x of I, where x of I is the sample space of x and x equals to x1, x2, and so on up to xn outcomes. For continuous distribution, this is the formula. Here we are using summation, and here we are using the integration symbol. Integration symbol. So this is the pseudocode for KL-UCB algorithm. First, we need to initialize the actions and time for each action, such as A of I, where I is equals to 1, 2, 3, 4, A1, A2, A3 actions are initialized with the time step T of A equals to 1 for each action, and X of A is a sample reward, and N of A is number of times that action is selected or that arm is pulled. So we have to repeat for each time step T, and for each action or arm A of I, we need to calculate the KL divergence, we need to calculate the KL divergence for current distribution and its updated version. where x of I is sample reward by number of times the action is selected. It is the current one and it is the updated one. We need to calculate the KL divergence for this using this formula. Using this formula, we need to calculate, and then after calculating, we need to calculate the upper confidence bound. And after calculating upper confidence bound for each actions, we need to choose the action which is having the highest upper confidence bound. Observe the reward R of T after selecting action T. So we'll observe the reward value while we select the upper bound, the highest upper bound action, and we'll be observing the reward, and then we need when then we'll be updating the estimate where see we are updating all this. We are updating time, we are updating the number of times the action is selected, and reward value also we are updating here. Time step is T of 8 plus 1 means time is increased and the action is also increased by plus 1. So here the x of a denotes the value after n of a selections, where this is n of a minus 1 to x of a means previous mean reward value of n minus n selections, and R of t is reward received in the n by 8th term selection, where n by n of a is number of times the action A is selected. In KL-UCB algorithm, it balances exploration and exploitation by adjusting the upper confidence bound based on the KL divergence. So as I already said you, it is main aim of the KL-UCB algorithm is to balance the exploration and exploitation and to solve the multi-arm bandit problems. So the choice of the function solving KL is important. KL-UCB algorithm is important, and it depends on the specific RL problem and the properties of the reward distribution. So as I already said, KL-UCB is more advanced than UCB in handling uncertain reward distributions, but it takes higher computational costs due to solving KL divergence. So we will be discussing some key points in KL-UCB algorithm where it uses scale divergence. First one is it uses scale divergence method, and scale divergence method is a measure that it is used to measure the difference between the empirical distribution of rewards and the predicted distribution. And it uses and this algorithm. Second point is the algorithm computes an upper confidence bound for each arm or for each action, which represents the maximum potential reward. And the third one is it is used to balance the exploration and exploitation trade of KL-UCB, balances exploration and exploitation by selecting the action or the arm with the having the highest UCB value. And arm selection, the algorithm selects the arm with the highest KL-UCB index. And the third other point is update. It after selecting each action, it is used to update the values like rewards and actions and time. It will be updating it. And it also, the algorithm computes scale UCB index for each action, which represents the maximum potential reward minus the KL divergence between the empirical and predicted distributions. And at last, convergence. So KL-UCB converges to the optimal arm or action as the number of iteration decreases. So that's it for this video, and thank you for watching.